So, welcome again, session number 2. This time we'll take a look again at PCB antennas using this kit I made. I can show you again this kit. We'll also go a little bit over where this kit actually came from. There is a nice study that we'll go over. I will show it, which looked at or simulated all of these antennas, and then we will take a look at tuning and matching today. So the study that I mentioned, I showed it already last time, was sponsored by Neocortec, written by Harald Naumann from Antennity. And we can take a quick look. You can download this study for free from his website. There is a link here in the descriptions. Sakshi, you can also post it into the comments so people can directly download it. And what does this study look like? So I have it here open. We can take a close look on the table of contents so you get a idea of what this study is about. So in this study, it's all about do-it-yourself antennas. So PCB antennas that are placed on the board that cost nothing, €0. Maybe you need one or the other matching component at the end, but copper on a PCB is basically free. And in this study, it is explained how to choose an antenna. So antenna parameters, which are important, and also certain things that you have to take care of when you design PCB antennas. And then there are several antennas developed. So there are the classical L antenna and F antennas in various shape, and also dual F antenna. And this is all compared to Texas Instrument design node. So Texas Instruments has quite some interesting design documents on PCB antennas, and they compare in this study these various designs with the TI design. So the boards I made, they are not the same size. Then the board here, not always at least, it depends. So they try to make it somehow comparable. And then it's looked into different parameters. What does this how the antenna is affected? For example, device size, device device size or casings, and this is all done using simulations. So why does it matter for Neocortec? Of course, Neocortec is interesting technology, mesh technology that is available on ISM bands. And right, so you can have it on 868 megahertz, for example, and all the antennas that are covered here are mostly 868 megahertz. So you see some explanations, illustrations about various important parameters. Here you see a simulation result, and then you also get to see some comparison with this TI design node antennas. And then it just starts. The study starts. It's just basically antenna shapes with different parameters that are played with, like here the distance of the radiator of this L antenna to the ground plane, and then basically how it affects the return loss, for example, which is really interesting, which we'll also look at. And yeah, there's a lot of interesting comparisons. So how thick is the feed point, various structures. You can see this for the band F antenna. What do you see here? Yeah, the distance of the location of the feed point, or the distance of the short circuit pin, which is a part of an F antenna always, will have an effect on your layout. So this is a really interesting study. PCB size, you can also see that later, and all kinds of variations that are simulated here. It's a very, very interesting and helpful study if you plan to develop IoT devices. So, and yeah, there's this nice simulation here with this S antenna. So it's an inverted F antenna that has this S shape, and you can see it actually here. When I switch to my desk view, then you see this board here with, let me grab something, this S shape. So it's just a normal F antenna that is basically bent several course. Yeah, the radiator length for this wavelength for 868 megahertz does not fit like this. So ideally you would have a wider board, right? And then you would just have the radiator with only one band. And but often that's not possible because the device size is constrained. So you start to bend it. There are also other types, of course, like this meandered shape is one way to do it. It's a different way to do it. Then you can see the band F as a real PCB, the dual F, and of course this L antenna, which maybe we look into in another session. I don't know. So this is all about this study. So I've turned them into real PCBs. These PCBs, yeah, they are available on our website. You can purchase them as a kit. They are all documented. So we set up a wiki where you get all the layout data, measurement data that I did. And yeah, the layout data is available in KiCad and Altium Designer. And of course, you can use these designs in your personal projects or commercial projects. But it's also a great tool for learning if you are new or unexperienced with PCB antennas. Then this is a good playground basically to see what happens. And I use them here to make some experiments. Yeah, this is the wiki that I already showed last time. So all of that is documented and it will grow over time. We will probably add other antennas as well. And yeah, so all the information is there. So last time, this is a screenshot from last session. What you see here is a program called Detune, where you see basically the return loss or two return loss curves, and this blue curve. This was the antenna as is on in air basically, or the PCB in air, and the other curve we created by just putting the antenna into a casing. And I can try to do that here as well. Oh. So as you can see, we have here our setup again. So we have here the nano VNA, so a vector analyzer that is very cost effective. It goes, I think, up to 4 gigahertz you can measure with this. It's a 2-port measurement device. We will today make only 1-port measurements. You can use the other port as well for 2-port measurements if you want to, for example, measure the isolation between antennas, or you want to see how your filter networks work, then you would do 2-port measurements. Right. And you see the antenna is here, and now I can switch over. I'm just realizing I need something else. Let me just try to switch to this screen. Okay. So maybe I can add this screen something. Let's see. I want this and this to be, yeah. Face is not so important. Aha, okay. So now we have this live, and we have this software which is called VNA View. This runs natively on Windows and Mac and Linux. And yeah, I just connected my VNA, and I just see that the antenna is connected. Ah, yeah. Okay, and then I'm not sure if I saved my calibration. I did. So, and what you see here, if we also change a little bit the graph limits. So I didn't do that in advance, but the advantage of you seeing me doing this is that you also see how I use this software. Ah, yeah, nice. Okay. So you can see this antenna. This actually, when I move this marker, I don't know if you can see it. This specific example here is resonant at 852. So it's also not a perfect match on the frequency that we want to have, but it's very close to, yeah, what we actually want. And now what happens, this is what we already saw last time, and we can also play around a little bit more. I have this plastic enclosure which I 3D printed, and yeah, first of all, you can see, of course, the hand effect. So when I touch the PCB, of course, the antenna changes. And if I put it in a plastic enclosure, then you can see that I will add a new marker, that of course the frequency goes down, the resonant frequency. So we were originally, this point was resonant with 852 megahertz, and now we end up 50 megahertz or round about. And we explained the last time why this happens. It is the plastic enclosure that changes the surrounding epsilon r, or the effective permittivity, and because it's not just surrounded by air, right? A part of the electromagnetic wave always goes through the FR4, and some other part goes through the air. But now we added some material around it, which has a dielectric constant, and that is different from air, and this is why the antenna becomes electrically longer. Yeah, you can see when I go close, right? It moves the hand effect. Okay, so this is what we all saw last time. So now what can you do about that? Because usually devices have enclosures, and yeah, we need to deal with that somehow, right? So what you can do, of course, is you can change the position of the device in the enclosure. It's maybe one thing that we can try to do. So I have here another casing that's slightly bigger, right? Slightly longer. And I have here like a big cutout, right? So I can move the board in there, right? And so this is the same result as we just saw. Didn't change anything, but when I move the thing, for example, further away from the topmost edge of the enclosure, it changes already a little bit, but not too much. Why is that? Because we still don't have air below the antenna. We have still plastic below the antenna. So I have some other tools I 3D printed, basically some space holders. And of course, you can try to lift up the PCB a bit, right? And then you can see that, we are getting closer to where we were, because in the near field, we now again have a little bit more air and less of this plastic dielectric, and this already helps. So it's really important when you design devices with an enclosure that you also position the device firmly in a certain point, because when you move it in the device, if there is space to move it, then of course your antenna starts to change, right? So that's why you mount it, not just put it like this. Okay, so this was all stuff that we saw the last time. I will now try to, did you actually see what I did the whole time? Yes, you see. So, okay. So this is not, of course, all what we can do. That would be a little bit not so interesting. So we have basically another a technique that we can use to, to deal with this. And these are often also confused, I saw. So that's why I made a short slide to explain it in very simple terms. So there is tuning and there is matching. And we will do today something that is sometimes made, but it's not good, which is to use matching to move the center frequency. Yeah. So tuning means you change the length of the antenna, the electrical length of the antenna, to resonate at the frequency you want. So you see this here on the left side. You have this orange curve. It's resonant somewhere because you put the PCB into a casing and you want it to be resonant at the area where you see this gray bar. So the frequency needs to go higher. So you have to shorten the antenna radiator. And there are different ways how to do that. One way, which is of course really obvious, is you just cut it. You make it shorter, like physically shorter. There are also other ways to do it. It depends on your antenna design that you use, but with this S-IFA antenna, you can also do it in a different way, which we won't do today, but we can scratch on the surface of the idea. Yeah, and the other thing, matching, this is basically making the antenna impedance, or to match the antenna impedance with a network. So antennas, they don't just have 50 ohm impedance. For example, the L antenna, we can actually look at that if you want. You will see that it's not close to 50 ohm. And this is why you then use matching. So if I just do that maybe shortly. So if you want, you can look at the L antenna as well. And you will see that it will have some sort of resonance, but it's far from 50 ohm. So you see on this graph here that you have a dip. It's very wide band now, right? So the matching circuit on these PCBs is only populated with 50 ohm, 0 ohms resistors. There are no inductors, no caps, no shunts, just the series components of the matching, yeah, populated with 0 ohm resistors. 0 ohm resistors have also some inductance in reality, but let's ignore that, and you can see that it has this shape. So there is something, but the antenna is nowhere near 50 ohms, right? That is, here's a 50 ohm in the Smith chart. So it would need to resonate here. And the way to get it there for a certain frequency, this you would do with matching, right? So just that you saw this antenna. So back to our original. Where's the antenna? I have too many boards on my table. So yeah, back to the antenna in the casing. Okay. So you saw this. So now we'll basically start with tuning, right? So right, so these antennas, these are F antennas, and they are quarter wave antennas. That means they have the electrical length of these antennas is a quarter of the wavelength of the frequency that they should work with. And the shorter you make the radiator, the higher is the frequency. So what we can do basically, so when you measure this antenna shape, actually this bigger. So when you measure the length of this antenna, I did that. Then you can see it has a length, the radiator, of 80 millimeters. And okay, this might not be the exact same antenna because I want to cut it live that I used to measure this. But when I measured it, it was 808. Yeah, there is missing an X, a multiplication. So 80 millimeters is the length. And at this frequency, we had 808 megahertz. We want to have 868 megahertz. So the length that we would need the radiator to be if we cut it is about 74.5 millimeters. So we need to cut it by about 5.5 millimeters. So, and what we can do, and I will now probably switch between various screens all the time, I guess. Yeah, I will just cut it live. So I have here such a tool. I also have some knives, right? And you can maybe see, I try to show it to you close up, is that I already measured this 5.5 millimeters. So there is on the PCB, there is a scale, millimeter scaler that you can use to yeah, exactly for this purpose. So I don't need a ruler. It's on the PCB, and I can try to cut it, right? I will use this tool, and I will not cut it directly, completely. I will make it step by step. So I take this guy, and then I will see something, yeah. So here's the radiator, and I will try to make some sort of cut. I need to go here. So now I've taken away roughly, 1.5 millimeters. And I'm stupid to not have saved the data and looked in Attune to it. But I guess I have one. So, rip. Aha. So now if I add another marker, we are around about 828. So it just moved about 20 megahertz up. We're just cutting 1.5 millimeters, which is great. So we can export this, and I have quite some folders. Folder. And is this good? Maybe not. Okay, so I've cut. So this is the S antenna minus one. Gosh, I know I can do this. Yeah, I just call it 1 millimeter. Doesn't really matter. Or maybe I call it 2 millimeters. I don't know. 2.5 or 1.5 millimeters. So now I can then shortly look at it. So this is now all in the casing, of course. Yeah. So we can scratch and scratch and scratch and scratch more. So I will take a little bit more. Let's take this one. No, it's not perfect, but I guess you can see it. Maybe. Yeah, you can see that there are some scratches. So now I have 1, 2, 3 millimeters roundabout. So, and yeah, we moved up even more, of course. Okay, this is to be expected, I guess, you know. So 831 millimeters. So I will also save this. And then, yeah. Naja. So this is about 3 millimeters. It's very rough estimate. So, and maybe one last cut. Okay. And now try to hit the sweet spot. So 5.5. Oh. Yeah. Ooh, that is quite beautiful. Oh, now this was really, how do you call it? In German, we call it Punktlandung, so a point landing, literally translated. So this is 5.5. So, and now that we are in Um, where is it? Oh, yeah, here, and then tuning, and then we can maybe, do I have another one which isn't cut yet? Of course not. This was my last example. Okay. Yeah, and then we can look at these curves. And I don't like the colors. Just load it several times. It's my way to deal with it. Gray, or green. Oh, yeah, okay, this is okay. I'm too lazy. You can also change the color in Attune. So this software is called Attune. It's actually for Windows. I run it on my computer using Wine. So that's working. So you can run it basically on Linux and macOS as well with Wine. And yeah, you can also change the color. We clear this. If you go to inspect, and there you see the measurement data, and then you can also change the color here, for example. I wanted to have this more orange, then the curve becomes more orange. So this is the 1.5 millimeter cut. So antenna length minus 1.5 millimeters. The purple curve is the other one, right? And then you get this one. So this is basically what tuning is doing. Next time 3 windows. Yeah. So this was antenna tuning live. And now I see that the time is again too short. So I will do the matching in another session. I think it's only 10 minutes left. I'm not sure if we have questions. Let me just check. And then we will do the matching in another session after my vacation. Okay, there's only one question. Okay. Let's see. Sure. So if you have more questions, then yeah, drop them into the comments. Okay, there's only one question. Then I will take, you can drop more comments into the chat. I can shortly explain then, yeah, what we would do with matching. So this thing that you saw, I'm seeing this thing that you saw on my on the VNA view, the Swift chart. This can be actually used to matching. This was a question that I got last time, like how to basically do that. Yeah, and what you see here, you see some point. So this chart just shows an impedance in a certain way, and you can use certain lines. So I think if I go to this Smith chart, then you see more curves here. And if I just, let's say, let's take an antenna that is, this is really close, right? So this is perfect. It doesn't need any matching. It's good as it is. But if you see something like this, so you have your frequency, your antenna impedance is up here, you would like to move that down to this 50 ohm, and you can do this with a matching circuit. And this circle, and this is where you want to go first, and you can basically use L and C components in series or as a shunt to move along these curves to reach your target. So this is exactly what you would then do here. You would add some series capacitance to move down. So this down here is the capacitive area. If you add capacitance as a shunt or series, you move basically down. You can move down this way, you can move down this way. So this is the series C moves down here. You hit this circle, and then you would move down here to the 50 ohm by adding another shunt. So this is the series C, moves down here, and this is the shunt, moves down here. Then theoretically, you should end up in this 50 ohm. So this is the theory behind it. Okay. We are planning an IoT Academy, so a deeper course, online course for embedded developers who often don't have the experience on even how to measure or how to work with PCB antennas. Yeah, we want to teach you everything of the fundamentals that you need to understand. It's very hands-on, so our goal is that you actually can measure antennas, that you can do calibration, that you learn different techniques how to do it, that you also see the pitfalls that you do, that you encounter. And yeah, this is currently planning, and we have here a link for a pre-registration. And it's a non-binding registration. So just we want to gather some people so that it makes sense. It's an online course, and in order to pay for the efforts to prepare all of this, we have a fee that we think is reasonable, is doable for many people who do this professionally, but also not too high. And it also covers all the preparation, all the exercises that we do there, all the time we spend, and also that we invite the one or the other person. Please let me know if you have suggestions for this or questions about it. Just let me know. You can register here. The link will be posted also in the comments, or you scan this QR code. That would be really great. Then we will contact you once we have more information when it can start. So as of now, we have one question. The simulations are done with HFSS or CST. So in this study, CST is used. That's what I can say. No HFSS. Yeah. Okay. Are there maybe more questions? I know that I can. Many questions. Harald is answering all of them. Hello. Software used measurements open source. Is the software used for measurements open source or licensed one? So this, I know this Attune is not open source, but it is free. I know, I just have to. Okay. Actually updated it. So the software we use, so this software that you see here, VNA View, this is open source. There's also other open source software to work with VNAs. This is very simple. Attune that you saw here is not open source, but it's a free software. But you could also use, I might take a look into doing that with Python. There's a scikit RF library, which I have been playing around with. Maybe make a session about that. Right, I will just try to there's so much in the chat, I can't do that. I have to get the questions here. Okay, does a magnet nearby affect the radiator? I had an IoT product where two halves of the product were connected using a magnet. So anything in the near field will affect it. So I don't think specifically it matters if you choose um, magnet or not. For sure, magnets will. But let me show you one thing. For example, so we have the thing in the casing, and let's take anything I have here. A LiPo battery. Just add it. Whoop, and it will affect the battery. You can take anything. You can take, and it depends on the battery. It's not always the same. So what it will do, it will electrically load the antenna, right? And it will change it. So everything will change the antenna, since the whole board is the antenna. Open source, I answered this. Will we get the certification at the end of that training? Yeah, why not? Whatever a certification is, but yeah, we could give you a certificate at the end. It's an interesting idea. I will see if there is somebody. So we plan to make exercises as well. So my idea is that it's like very hands-on, and that we use these kits that we have to play around with, right? So that you really learn, also make the mistakes, or see the mistakes, or see what happens. Yeah, in between the sessions, we have always 1 week, basically. So 1 session per week for 2 hours. So there's enough time to actually practice, and then also ask questions that we can answer in the online sessions, right? And why not a certificate? I have to think about what is written on it, but it's a nice idea. I like it. Could you please show me how you adapt the antenna to achieve the desired performance in a specific frequency band? From what I understand, the initial design of the antenna generally is outside the target frequency band. You then carry out an adaptation or optimization step that allows to shift the resonance frequencies toward the desired band. Could you explain to me in detail this adaptation procedure? I would like to understand why the antenna does not work directly in the target band from the first design without adaptation step. Yeah, what are the physical phenomena, geometric parameters that are reasonably for this frequency shift? Yeah, so the antenna is not just, so first of all, the antenna is not just the radiator that you see on the board. So it's not just this, it is the whole board. The whole board is radiating. If you change anything on your board, then your antenna changes. It's also about the material that is inside. So if you use FR4 dielectric, it's not very, it can vary with its dielectric properties. So you can also, it's also important when you really then make a product that you mass produce, basically, that you have a vendor for the PCBs that offer you kind of, yeah, a very stable or the same dielectric. Because if they change it in between the material, then suddenly your antennas don't work anymore. For really high frequency stuff, also FR4 is too unstable, because this is basically a very rough material. If you ever cut it open, right, you will see the fabric. So if you want to have very accurate antennas, you would use another substrate, like Rogers substrate, for example. the antenna radiator is usually made longer than usual in the design because you want to make it shorter. Shortening then the antenna is always easier than making it longer afterwards, obviously. And yeah, anything will affect your antenna, as we have just seen, the battery that you place there. So you can also start with simulation, of course. So there's tools to make simulations because it can cost you quite some time to carry that out physically always. But simulations are also very limited. It's a good start, and then you need to, I think, always have a board to play with, like to really measure, because you cannot simulate everything that is in there. Yeah, you will not have the perfect model of your battery for your simulation and so on. I hope this answers the question. Yeah, there are different techniques to change the frequency. So we now cut the radiator. If you read this white paper, there's actually you can actually see it here. This blue thing here, and this is basically a way to add a tuning capacitor, right? So you can add the tuning capacitor on this radiator. This is possible, and then you also make the antenna electrically shorter, right? So it's another way of cutting. Advantage of using components like this, you can switch them, right? If you want to have a product that uses these antennas and works in the US at 915 megahertz and in the EU, for example, 868 megahertz, you can make that with a single PCB with the same radiator with switchable components, basically. Yeah. So to the right, respectively, the SVR standing wave ratio drifts away to the right. What can be the case? So that means, if I look at some examples, we have this antenna. So this is the S11, and then look at the standing wave ratio. It shifts to the right, means the antenna radiates, or it doesn't really radiate better, but you have lower reflections at a higher frequency. Okay, what could be the case? Yeah, I don't know. I have to I have to see the setup. I would say standard ESP32 boards. Yeah, I don't know how these standard boards are implemented, and I know ESP32. So if you use these boards with modules with antennas inside, yeah, I would also be very curious. I don't know how they lay out their antenna or how they optimize it, right? Because yeah, you have to look maybe into the documentation. I don't know Espressif's documentation about their PCB antennas in the modules. But ideally, of course, they have information about how to use it, because I mean, you have a module, you put it in a PCB, you want to have it in a casing at the end, probably. So maybe the manufacturer of this board accounted for I don't know, an enclosure for some dielectric. I can't tell you this, but this would be a guess, you know. Maybe you have to look into that. Okay, I see we are 5 minutes over time. Thank you very much for your attention. It's really nice that so many people like what I do here. I hope it's really valuable for you. If you have any questions, or you, I don't know, you have feedback also, or ideas, what I should look into next, then yeah, please reach out to me on LinkedIn with a message, or you can also use this email address, iot-kitchen@embever.com, and yeah, there you can also send some stuff if you like. Okay, thanks, and I wish you a wonderful day. Bye bye.